We began our project by taking a large, obvious idea that we favored from discrete mathematics, Hamilton cycles. A Hamilton cycle can be drawn by following paths such that every point along these paths is touched and that the line must return to the starting point to create a cycle. However, no path may be used twice. Thus, there isn't a Hamilton cycle for every graph. It must have enough paths to provide a route to each point and back to the beginning. For example, every point must have at least two paths, otherwise you must use the same path twice and touch a point more than once.
You may have used a Hamilton cycle without realizing it. Maybe you went to a theme park and wanted to ride every attraction once. However, because queue lines can take some time, you wanted to take the quickest route between each ride, never needing to cross back over the same paths. Since you start at the entrance, a logical sequence might be going directly to the bumper cars, then to the drop coaster, then to the Ferris wheel, then to the coaster fiesta, then to the inertia ride, and when you've finished, you can go straight back to the entrance to leave. You've made a Hamilton cycle. Coming back to our project, we started with some brainstorming, drawing random graphs that looked interesting and possessed Hamilton cycles. We came across a type of graph that carried a pattern we deemed intriguing. The graphs look like this one, a polygon inside of a larger polygon connected at the corners. We tried putting one polygon inside of a different type of polygon, such as a triangle inside of a square. But as you can see, because of the difference in amount of corners, we have to draw in an extra edge or leave one of the outer corners disconnected from the inside figure. Though these are interesting, we did not care much for them, so we made the rule that the two polygons must be the same. Then we set to work finding every possible Hamilton cycle for these graphs, from a triangle inside of a triangle to an octagon inside of an octagon. Our problem to solve, whether there exists a pattern to create a formula that can predict the amount of possible Hamilton cycles for one of these given graphs. After looking at our results, we noticed a pattern. For the polygons with an even amount of corners, the squares, hexagons, and octagons, the amount of possible Hamilton cycles is equal to the amount of corners in the type of polygon, plus 2. So the squares had 6 possible solutions, the hexagons have 8 possible solutions, and the octagons have 10 possible solutions. For the odd polygons, the triangles, pentagons, and heptagons, the amount of possible Hamilton cycles is equal to half the total corners in the figure. So the triangles have 3 solutions, the pentagon have 5, and the heptagons have 7. Before continuing, I'd like to point out that for these graphs, if we were to draw the simple case, the single shape, such as a single square or triangle, all of the polygons have just one Hamilton cycle. Our results from drawing the cases of a single polygon within a like polygon led us to make our first official hypothesis. We suppose that if we drew a third polygon around the two other polygons and connected the corners of that polygon to the middle one, then the equations we found for the two alike polygons would predict how many possible Hamilton cycles we would find for each case, triangles, squares, pentagons, and so on. If you notice, we shade in the Hamilton cycles to better visualize them. So if we draw 3 triangles and connect them at the corners, we would expect half the amount of solutions as there are corners in the figure, but there are 9 corners which cannot be divided evenly. We found that there are 6 possibilities, which is 2/3 of the 9 corners. To verify this, we tested the pentagons and found 10 possible Hamilton cycles. We also tested heptagons and found 14. So from this we hypothesized that for odd polygons drawn as these graphs, the amount of possible Hamilton cycles must be the amount of polygons minus 1 over the total amount of polygons multiplied by the total amount of corners. Now that we have found a new pattern for the odd polygons, let's consider the even polygons. Square within a square within a square yields 22 possible Hamilton cycles, which doesn't follow the equation we had expected. So let's consider a square inside of a square inside of a square inside of a square. But first, let's define these graphs in a way that is easier than this tedious repetition of polygons inside of polygons. Let's call them mirror graphs of n, where n represents the number of polygons in the figure before they are connected. This is a mirror graph of 3, and this is a mirror graph of 4. While drawing these, we found it most effective to find a Hamilton cycle, then turn it until it repeats itself. Each of these are valid Hamilton cycles, and we call them rotations. We also found that if you draw the reflection of the original Hamilton cycle, it makes another new, valid Hamilton cycle, a sort of mirror reflection of the original. We call this a flip. The flip Hamilton cycle can also be rotated to identify more Hamilton cycles. This saves time that we would otherwise be using to find them individually. What's kind of cool about the symmetry of these graphs is that though both odd and even polygons may have symmetrical Hamilton paths, that is, they may be cut into 2 equal parts, the Hamilton cycles for even polygons always have at least one symmetrical path that can be rotated less times than other Hamilton cycles before returning to its original position. We cannot flip it either, because it results in the same Hamilton cycle. Because we color in the Hamilton cycles to make it easier to visually see the different cycles and no repeats are made, we came to another interesting point. Hamilton cycles from a smaller mirror graph fit into a Hamilton cycle of the next bigger mirror graph. We don't know what it means, but it's pretty interesting. Anyway, for the square, the amount of Hamilton cycles for the mirror graph of 4 is 66. Here's a complete table of our findings. Instead of calling a triangle, we have denoted it as C3 and a square as C4. The C in number represents the number of corners in the cycle. So a pentagon of mere graph 2 could be denoted as C sub 5 mg2. We wanted to derive a formula from patterns in the table, but have been unsuccessful in finding a formula that would determine the amount of solutions for any mere graph or polygon. We know that whether the amount of corners of a polygon is important because whether it is even or odd affects the pattern of the amount of possible Hamilton cycles. There may be an equation for each mere graph event. For mere graph of 2, even polygons have as many possible Hamilton cycles as 1/2 the number of corners in the graph, plus 2. Odd polygons are equal to exactly 1/2 the amount of corners. We also know that for MG3, the odd polygons C3, C5, and C have as many possible Hamilton cycles as 2/3 the amount of corners in the figure. Graph of 3 even polygons. We could not find a formula. However, we did notice an interesting pattern in the even polygons that would be fun to pursue. The amount of possible Hamilton cycles for an even polygon, let's take the square for example, which is 2 more than a number divisible by 2/3 the amount of corners in the graph. 20 is divisible by 4, likewise 66 is divisible by 6, and 168 is divisible by 8. As you can see, there is much left to be explored.